Hello and welcome to this tutorial about assigning boundary conditions and accounting for trapped powder. The objectives here are to assign thermal and mechanical boundary conditions to the build plate and to account for trapped powder in the analysis. We start by opening a saved TIVIS project. On the Home tab, we click Build Plate and open the Size tab. Our first task is to enlarge the build plate. We're going to change the length to 50 millimeters in both X and Y directions. Now to set a thermal boundary condition, we go to the Build Plate Properties tab to review the heating options. We see three of them here. None would be no thermal boundary condition. Just start at room temperature and allow the build plate to absorb the heat of the build. Initial temperature means to assign a particular temperature at the start of the build but not hold that temperature. The third option is controlled temperature, in which you set a temperature that will be maintained throughout the build process. And the temperature field here is used with the initial temperature or controlled temperature selection. Plate fixture is a mechanical boundary condition with three options. Fix build plate base, symmetry on build plate faces, fixes nodes on the base of the build plate, at the center of the build plate in X, Y, and Z directions, and constrains all other nodes in the Z direction. Simulate bolt release simulates the effect of bolting down each corner of the build plate for the deposition process, then allowing the part to cool down to room temperature and unbolting the build plate. The third option, fix the center of the build plate, models the case of a build plate held in place on the build platform by gravity and friction alone. For this tutorial, we'll select a controlled temperature of 100 degrees Celsius and a fixture setting of simulate bolt release. Hit OK, click Solve, and save the project where you'll be able to find it again. When the results are loaded, play through the temperature results. You can see that while the part eventually overheats, the build plate holds the set temperature until the end when it cools down to room temperature. Now that we've seen the effects of boundary conditions on the build plate, let's examine the effects of such conditions on the part. The default thermal boundary condition for the part is a heat flux or energy loss to all exterior surfaces, which simulates the effect of losing energy into the surrounding powder. But if parts are close together on the build plate, rather than dissipating that energy, they might heat up the powder between the parts. This temperature gradient can actually affect the mechanical response. So for greater accuracy, we need to simulate all of the loose powder in the analysis, and we have a way to do that. On the Home tab, click Operating Conditions and set the thermal boundary condition to conduction to loose powder. With this setting, we simulate the entire loose powder bed. Hit Solve to overwrite the previous results. When results appear, this time play through the temperature trapped powder results. Now, as we walk through the results, we're adding elements for the entire powder bed and simulating conduction into that material. You can see extra powder added to the analysis, which is simply a way to speed up run times by making the mesh more coarse in the build plate away from the part. Coarsening has to be done in 3 dimensions, so if we want to do it in the X and Y directions, we also have to do it in the Z direction. Now to summarize what we've covered in this tutorial, we set a controlled thermal boundary condition on the build plate. We simulated the mechanical boundary condition of build plate cooling and bolt removal. And we added loose powder into the analysis to improve the accuracy.